Hello everyone, welcome to the week 6 of the problem solving session for the course Material and Energy Balance. And we are almost halfway done with the course. So this week we will quickly brush up a very small concept in material balance and then start with energy balance topics. So briefly about myself, I'm Aushandra. I'm a PhD scholar, the Department of Chemical Engineering, IIT Kanpur. And if you have any queries related to the course, feel free to reach out. And also, I urge you to use the course discussion forum to post your queries. Every Saturday from 3 to 5 p.m., we are meeting for the past 6 weeks. Today is the sixth week lecture, and you will find the recordings of these meetings in my YouTube channel. The notes are also shared after every session. So for smooth ambience of this class, I request you to kindly keep yourself muted. If you have any queries, you can unmute yourself and ask. Otherwise, the chat option in the meeting is not available. So this week we learned about what is stoichiometric matrix. So these matrices are very much useful when you're trying to do material balance problems for a complex system like a metabolic pathway where multiple reactions are involved and you want to do material balance for different components involved in that reaction. So in that case, we can write a simple material balance equation or a flux equation first. This is the reaction flux equation where ds by dt, which is the reaction fluxes or the rate of the reaction, is given by the dot product of the stoichiometric matrix N and the uh, individual reaction fluxes. So ds by dt represents the rate at which the metabolic concentration is changing, right? ds by dt is the rate at which metabolic concentration is changing, and it is given by n dot nu or v, which is the rate of the reaction. So at steady state, ds by dt becomes 0. So nu dot v is 0. So how do we write stoichiometric matrix? So stoichiometric matrix is basically a matrix of m by n, where m represents the number of metabolites involved and n represents the number of reactions involved. For example, if this is a complex reaction with 5 metabolites, S1, S2, S3, S4, and S5, and the rate of reaction for this particular reaction is V1. So there is only one reaction involved. So we will write a 5 by n matrix. Now, since this is stoichiometric matrix, so we have to take in account the stoichiometric coefficients for each of the metabolite in this particular reaction. So this particular matrix can be thought of like this, where S1, S2, S3, S4, and S5. And for reaction V1, we have to see what is the stoichiometric coefficient. In the reactant, for reactants, we write stoichiometric matrix with the negative sign. And for products, we write the coefficient with the positive sign. So S1, S2, and S3, these are all reactants. So the stoichiometric matrix will be -1, -1, -1, whereas S4 and S5 are on the product side. So stoichiometric coefficient in this matrix will be +1 and +2. So when you complete this, you will get a 5x1 matrix, which looks like this. Similarly, when there is a much more complex reaction system, like for example, for this particular metabolic scheme, you see that there are S1, S2, S3, three metabolites involved, and three reactions are happening. So S1 participated into this network after getting formed from a different reaction with reaction flux V1. And then S1 is like getting changed into some unknown product. We are not shown here. But when that change is happening, we see that there's a conversion of S2 to S3 at a rate of V2. Similarly, S1 can also participate in another. Hello, am I audible?
Yes.
Yeah. So I just started the class. All right.
Okay.
So, okay, I just started. So I was discussing about the stoichiometric matrix and how to write a stoichiometric matrix. So these matrices are relevant when you're trying to understand the uh, reactions, multiple reactions at a time. For example, in biology, there are metabolic pathways involved where there are hundreds of reactions happening at the same time, and one substrate can become a product in another reaction. So it's a very complex pathway. So for those kind of reaction systems, we can understand the rate at which each metabolite is getting formed, right? The ds by dt, the rate of change of the metabolite concentration, we can represent as a dot product of n dot v, which is a dot product of stoichiometric matrix and the reaction flux or the rate of the reaction v. So stoichiometric matrix itself is a m by n matrix, where m represents the number of metabolites and n represents the number of reactions. So for example, this is your reaction scheme, all right, where three reactants are there and two products are getting formed. So for this particular reaction scheme, we can form a n 5 cross n matrix. So 5 represents the number of metabolites. So there are 5 metabolites. And since there is only one reaction, so it will be 1. So 5 cross 1. And into this matrix, how do we fill in the data? We basically look at the stoichiometric coefficients for each of these reactants and products. The stoichiometric coefficient will be negative if the substrate is on the reactant side. If it is on the product side, then stoichiometric coefficient will be positive. So we will form a matrix like this. So S1 stoichiometric coefficient is -1, S2 is -1, S3 is -1, like this. S4, since it is product side, so it will be +1, and for S5 it will be +2. So this is very simple to understand when there is only one reaction involved, right? So what happens if you have more than one reactions involved and there are multiple substrates as well? Like you can see one substrate will participate in multiple reactions. So how do we form this kind of a matrix in that case? So let's consider this example. Here what is it? Here S1 is coming from like some other reaction. It is a product of some other reaction which is getting formed at the rate of V1. Now S1 can either participate in reaction 2, or it can participate in reaction 1. Okay, so either ways it is possible. So give me a minute. I'll reshare my screen. Okay. Okay. So yeah, as I was saying, S1 can either participate in reaction 2 with reaction rate V2, or it can go about to participate in reaction 3 in this particular scheme. And in either of this reaction, two metabolite S2 and S3 is getting either formed or they are getting consumed. Okay, so we have to look at the arrows in order to understand what is the product and what is the reactant in this particular scheme. So one thing is very much clear, that there are three metabolites, M is 3, and there are three reactions involved, so N is also 3. So we will get a 3 cross 3 matrix. But we have to fill this matrix. So how do we fill it? So the metabolites S1, S2, S3, okay, their stoichiometric coefficients will form the rows, and in the column there will be reaction 1, reaction 2, and reaction 3. You can write as R1, R2, R3 as well. Okay, so this is how the 3 by 3 matrix will look like. So now we have to fill in the stoichiometric coefficients. So for S1, look, for V1, it is a product. All right, S1 is a product. So the stoichiometric coefficient will be 1. Then S1 is not, S1 is participating as a reactant for reaction 2. So from S1, some XYZ product is going to get formed. So it will be -1. Similarly, S1 is a reactant for reaction 3. So the stoichiometric coefficient will be -1. Then S2. Let's look at the substrate S2. So S2 is involved in both reaction 2 and in reaction 3. But in reaction 2, S2 is a reactant. Okay, so the stoichiometric coefficient will be -1. Whereas in R3, reaction 3, S2 is a product. So the stoichiometric coefficient will be +1. Now, since S2 is not involved at all in reaction 1, so stoichiometric coefficient will be 0 here. Similarly, for S3, if you look at it, S3 is a product for reaction 2. So stoichiometric coefficient will be 1. S3 is a reactant for reaction 3. So here it will be -1. And since again S3 is not at all involved in reaction 1, so it will be 0. So in this way, you can write a stoichiometric matrix for a complex network of reactions, right? Now, quickly, let's try to solve some problems, all right, based on this concept. So this is the first problem that we have. This is your reaction scheme given, all right? So quickly, let us see how many how many metabolites are there. So number of metabolites is 3, S1, S2, and S3. All right. Whereas how many reactions are there? There are 1, 2, 3, 4, 5, 6. So there are 6 reactions. So we will be able to form a 3 cross 6 matrix. All right. So let's try to write this matrix. S1, S2, S3. Here V1, V2, V3, V4, V5, V6. All right. Let's try to fill in the stoichiometric coefficients now. So for S1, since this is a product, all right? So you can see the arrows. The arrows are reversible, right? This is for the reversible reaction. So in this case, you have to consider that you will take one direction, let's say from left to right as your forward direction, and uh, right to left as a reverse. And you have to consider, you have to stick to only one direction, commit to only one direction when assuming whether the metabolite is a reactant or a product in a particular reaction. Since the entire reaction network, like, and each of the metabolites involved, they can be reversibly converted back towards a reactant state. So like we have to consider that all the values that we will write is in the same direction. So like this and like this. Okay. So this is my arrow direction based on which I'll put the positive or negative signs. Okay. So S1 is getting formed for reaction 1. So there will be +1. Then S1 is a reactant for reaction 2. So there will be -1. And then S1 is not at all involved in reaction 3, reaction 4. Then S1 is a reactant for reaction 5. So -1. Then S1 is not at all involved in reaction 6. Okay, so first row done. Second row for metabolite S2. S2 is getting, S2 is not at all involved in reaction 1, so 0. S2 is the product for reaction 2, +1. S2 is the reactant for reaction 3, so -1. Then S2 is not involved in reaction 4, S2 is not involved in reaction 5, S2 is not involved in reaction 6. Then for metabolite 3 or S3, S3 is not involved in reaction 1, S3 is not involved in reaction 2, S3 is the product in reaction 3, S3 is the reactant in reaction 4, S3 is the product in reaction 6, whereas S3 is not at all involved in reaction 5. So in this way, your stoichiometric matrix is complete for this complex network of reaction. Let's try one more time, but with this different reaction scheme. So here you can see that there are two reactions involved comprising a kinase and phosphatase reaction. So we have to write down the stoichiometric matrix for these reactions. So number of metabolites is 2, and there are two reactions. Okay. So N is 2 cross 2. Here metabolite is ATP and ADP, and there are two reactions. So let's complete this matrix. In the first reaction, ATP is consumed, all right, and in the second reaction, ATP is getting formed, so +1. Whereas ADP in the first reaction is getting formed, and in the second reaction, ADP is getting consumed, so there will be -1. So like this, you will get a symmetric matrix, all right, for this particular reaction scheme. Once again, let's practice. So here you are given upper part of glycolysis. You have to write down the stoichiometric matrix for this particular reaction scheme. So how many metabolites are there? Again, number of metabolites. There are 1, 2, 3, 4, 5, 6. 6 metabolites. And how many reactions? There are 3 reactions. All right. So what is the matrix? The matrix will be M cross N, 6 cross 3. All right. So this will be a tall matrix. S1, S2, S3, S4, S5, S6. There is V1, V2, and V3. So you will get a tall matrix like this. So let's look at each reactions and the substrates involved in those reactions and look at their stoichiometric coefficients in order to fill up this stoichiometric matrix. So for reaction 1, S1 is a reactant. Only 1 mole is getting used. So -1. Then in reaction 2 and 3, S1 is not involved. Then for substrate 2, a metabolite 2, it is a product. S2 is a product in reaction 1, and S2 is a reactant in reaction 2, and in reaction 3, it is not at all involved. Let's look at S3. So S3 is not involved in reaction 1 and 2. Sorry, it's not involved in 1, but it is a product in reaction 2, and it is a substrate in reaction 3. Then S4 is not involved in reaction 1 and 2, but it is a product in reaction 3. Now S5, so S5 and S6 both are involved in reaction 1 and 3. In reaction 1, S5 is getting consumed, and in reaction 3 as well, S5 is getting consumed. In reaction 1, S6 is getting formed, and in reaction 3, S6 is getting formed. So like this, you will get a stoichiometric matrix, a tall stoichiometric matrix, all right, for this particular reaction scheme. There's one more example here. So this is again a reaction scheme. You have to write down the stoichiometric matrix. So same procedure. You have to write down the number of metabolites. So there are 4, S1, S2, S3, and S4. And how many reactions? There are 4 reactions. 1, 2, 3, and 4. So N is 4 cross 4. For S1, S2, S3, and S4. So why I'm writing the name of the metabolites in the as a first row and then as its first column and then reaction number in the top of the matrix. This just helps us to visualize a stay in track with filling up the stoichiometric matrix. Like it helps us keep in track. You can, if you can visualize it, if you don't need to write it, then also it's fine. Your answer is basically, your answer won't have these additional row and the left hand side most row, left hand side most column, and the top row. Okay, these two won't be present in your answer. So these are just I'm writing for guidance. Okay, so that I don't stray away and write wrong stoichiometric coefficient in the matrix. Okay, just I wanted to make it clear. Right. So let me use a different color in order to make the distinction exactly clear for you. So S1 is again, there are reversible arrows involved. So we have to take one arrow, one direction, okay, constant. All right. So I'm taking this green arrows as my forward reaction. And based on this forward reaction, I'll consider like S2 is my reactant and S1 is my product, all right, for different reactions. Okay. So for reaction 1, S1 is the product, so plus 1. For reaction 2, S1 is the reactant. For reaction 3, S1 is not involved, whereas in reaction 4, S1 is not involved. Then if you look at substrate 2, metabolite 2, S2, S2 is not involved in reaction 1. S2 is the product in reaction 2. S2 is the reactant in reaction 3, and it is not involved in reaction 4. Then if you look at S3, S3 is not involved in reaction 1. S3 is the reactant in reaction 2. S3 is not involved in reaction 3. S3 is the product in reaction 4. Similarly, for substrate 4, S4, S4 is not involved in reaction 1. S4 is the product in reaction 2. S4 is not involved in reaction 3, whereas S4 is the reactant for reaction 4. So like this, you will get a stoichiometric matrix for this particular reaction scheme. All right. So here is another question, or the last question on this topic. So you are given again the upper part of glycolysis pathway. Stoichiometric matrix for this particular reaction scheme is given. You have to basically fill up the values of A1, A2, A3. So you are given a matrix a layout of a matrix containing 1, 2, 3, 4, 5, 6, 7, 7 metabolites and 3 reactions. So 7 cross 3 matrix you are given. Layout is given to us. And we have to basically fill in the values. So for clarity, I'll basically construct a new matrix for you. Now, if you look at fructose 6-phosphate in reaction 1, it is a reactant. Then fructose 6-phosphate is a product in reaction 2, and it is not involved in reaction 3. Then if you look at fructose 1,6-bisphosphate, it is a product in reaction 1, and it is a reactant in reaction 2, and it is a reactant in reaction 3. Then if you look at glyceraldehyde 3-phosphate, it is not involved in reaction 1 and 2, but it is a product in reaction 3. And if you look at ATP, so ATP is getting consumed or it is a reactant for reaction 1, and then it is not involved in any of the other reactions remaining. Then if you look at ADP, it is getting formed in reaction 1, and then it is not involved in any other reactions. If you look at water, it is getting formed in reaction 2. And if you look at PI, it is getting formed in reaction 2. So like this, your matrix would look like, and you now got the values of A1, A2, A3 as -1, 1, 0, B1, B2, B3 as -1, -1, -1, and so on. All right. So with this topic, we are concluding the material balance chapter for this course. From this slide onwards, we will start our discussion on energy balances. So energy balance can be done on both closed system as well as open system. Whereas when we were discussing material balance, we only consider open system. So quickly, open systems are those systems where mass transfer is allowed. So mass can enter or come out from the system into its surrounding. Whereas in closed system, boundaries are there, so no mass can get exchanged from the system to surrounding or from surrounding to a system. Okay. So, but energy, whereas on the other hand, can be exchanged from the system to surrounding in a closed system. So energy in the form of heat, work, it can get exchanged. So which is why we will study energy balances for both closed system as well as open system. So what's the energy balance equation for the closed system? So in this one slide, I tried to summarize the way we are going to derive the equation for the closed system. For detail, I would request you to kindly go through the video lectures, all right, for this week's video lectures. So general balance, if you remember, it is basically accumulation is equals to input minus output minus consumption plus generation. Now, since energy can neither be created nor destroyed, so the energy consumption and generation terms, they will be zero. So the final balance equation will contain the one accumulation term, and it will be equal to input minus output. So accumulation will be because of whatever energy is remaining in the system, means final system energy minus initial system energy. This will be accumulated energy in the system. And in and out refers to the flow of energy in and out of the system, or net energy transferred to the system, okay, in minus M. So the initial system energy will contain three types of energies: UI, or the internal energy; EK, or kinetic energy. Kinetic energy can also be represented with K, all right? And then potential energy, EP, or we can also write it as P, right? So this I've taken from one textbook where they have chosen to represent kinetic energy as EK, and um, potential energy as EP, whereas I saw in another book where they are using capital letters like K and P for the representation. Okay. Similarly, final system energy will be UF plus EKF plus EPF. So I subscript refers to initial states, and F subscript refers to the final states. And the energy transferred is that is the input minus output. That term is given by Q minus W. So when we replace these terms in this particular equation, we'll get this form. If we rearrange and replace these terms with delta U, delta EK, and delta EP, we will get this form. This is the final energy balance equation for closed systems. All right. Now, in this particular expression, there are some ways to simplify it under some circumstances. Now, if there is no change in temperature, there is no phase change or chemical reaction occurring in the closed system, then internal energy, the change in internal energy delta U, will be zero. If the system is not accelerating, okay, there is no net uh, velocity or acceleration associated with that particular system, then kinetic energy or the change in kinetic energy will be zero. The system is not rising or falling, means there is no change in the height of the system. Then net change in potential energy will be zero. If the system and the surrounding are at the same temperature, or if the system is perfectly insulated, means there is no heat exchange, then Q will be zero. If there are no moving parts or electric currents or radiation at the system boundaries, okay, so W, or work, will be zero. A few more things to note. We use certain sign conventions in order to represent heat and work. If heat is added to the system, then Q will be represented with positive value. All right. If heat is removed from the system, Q will have a negative value. If work is done by the system, then W, or work, will have a positive value. If work is done to the system by the surrounding, then work term will have a negative value. Yeah. So I hope these statements are pretty straightforward and easy to understand. So we'll move forward. Here are few simple questions based on what we just understood. So first question, mass does not cross the system boundary in, underline, closed or open system. So mass cannot cross the boundary in closed system. Okay. Now, if 250 joule is added to the system as heat, what is the value of Q? Remember the sign conventions that we just discussed. So Q will be plus 250 joules. Part C. If 250 joule of work is done to the system, then what is the value of W? Work is done to the system. So W will be minus 250 joule, right? The W or the work will become negative. If the closed system has internal energy of 100 kilocalories at the beginning of the process and 50 kilocalories at the end, what is delta U? So delta U is basically internal energy final minus internal energy initial. So at the end, there was 50 kilocalories and initially there was 100 kilocalories. So delta U will be minus 50 kilocalories. All right. Okay. This is another question that is based on energy balance on a closed system. Quickly have a read, right? So there is a gas in a that is contained in a cylinder fitted with a movable piston. So it looks something like this. It's a cylinder with a moving piston and there is gas inside it. Initial gas temperature is 25 degrees Celsius. Cylinder is placed in boiling water with the piston in fixed position. Heat in the amount of 2 kilocalories is transferred to the gas, which equilibrates at 100 degrees Celsius and a higher pressure. The piston is then released and the gas does 100 joule of work in moving the piston towards new equilibrium position. The final gas temperature is 100 degrees Celsius. So write the energy balance equation for each of the two stages of this process. And in each case, solve for the unknown energy term in the equation. In solving this problem, consider that gas in the cylinder to be the system. Neglect the change in potential energy of the gas as the piston moves vertically and assume that gas behaves ideally. Express all energies in joules. Okay, this is the question. So first, let's take case 1 where the initial gas temperature was 25 degrees Celsius. This is a cylinder. The gas is at 25 degrees Celsius. It's the initial state. And then the cylinder is placed in boiling water with piston in fixed position. Then the heat is transferred to the gas, which equilibrates at 100 degrees Celsius. So the final state is the cylinder remaining at its initial position, but the temperature of the gas increases. And in this particular state, heat Q equals to 2 kilocalories is transferred. Okay, so in this case, the energy balance equation will become this is the general equation, but we will simplify this first. We were told to assume or neglect the change in potential energy. So delta EP will be 0. All right. Q is 2 kilocalories, which is known. The kinetic energy will be also 0 because the system is stationary. There is no acceleration or anything like that. And work will be also 0 as there boundary, there is no moving boundary. There is no moving boundaries. Gas is not doing any work in order to move the boundary of the cylinder. So this means delta U is equals to Q. Q is 2 kilocalories. Now we were told to express all the energies in joules. So we have to convert kilocalories to joules. First, we know 1 kilocalorie is 1000 calories and 1 joule is equivalent to 0.24 calories. If you're unsure, you can look it up. All right. So this is the conversion. This is how you will do the conversion. And what you should get around 8370 joules. Okay. This is for case 1. Now for case 2, what we were given, the piston is then released. This is case 2. Piston is then released and gas does 100 joule of work in moving the piston to its new equilibrium position. So now the initial state is having gas at 100 degrees Celsius. Some work is done by the gas for moving the piston to a new position, which is work is equivalent to 100 joules. And the final temperature of the gas is 100 degrees Celsius. Now, in this case, how will the energy balance equation will change? This is the energy balance equation that we already know. right? Again, this part or kinetic energy is 0. Potential energy is also 0 with the same assumptions, right? Delta U is 0. Why? Because we are assuming, or it is given in the question, that gas behaves ideally. And for ideal gases, internal energy is a function of temperature only. So since temperature change is not there, final is 100 degrees Celsius, initial is also 100 degrees Celsius. So internal energy is 0. Okay. What we see, Q is equals to W, and W is 100 joules. So that's it. Okay. There. So this is another question that we have. Here we are going to calculate kinetic energy. So water is pumped from a storage tank into a tube of 3 centimeter inner diameter at the rate of 0.001 meter cube per second. What is the specific kinetic energy of water? All right. So we will derive this answer in the units of joule per kg. So how shall we start? So we know kinetic energy, K or EK, whatever you want, is half mass and V square. V is the velocity. So specific kinetic energy, basically we have to divide by mass. It will become half V square. All right. We are given, we are not directly given velocity. All right. But we are given the volumetric flow rate and we are given the inner diameter. So we can use these two quantities to determine the value of velocity V. So here we are given inner diameter is 3 centimeter. So radius is 1.5 centimeter. Velocity V is basically the volumetric flow rate divided by area of the tube is pi r square by 1.5. Okay, is pi r square. We have to make sure that units are correctly converted. So we know 100 centimeter is equivalent to 1 meter. So when we solve this, you should get the value in meter per second, because these 2 centimeter squares will get cancelled out, and this meter square will become cancelled out with meter cube. You should get meter by second. So when you solve the numerical values, you should get 1.415, okay, as the value of velocity. So kinetic energy, specific kinetic energy is equals to half V square, which is 1.415 square meter per second square. Now we have to get the answer in the units of joules per kg. So we know 1 Newton is equivalent to 1 kg meter per second square. And we also know 1 joule is equivalent to 1 Newton meter. So when we uh, remove the common units like centimeter square, then meter square, Newton. So we will be left with joule per kg. And when you solve this particular expression, the numerical values, you should get you should get 1. All right. Should get 1 joule per kg. So there you go. In this question, you have to label whether the properties that were given belongs to intensive or in extensive category. So quickly, what do you mean by intensive property or extensive property? Intensive properties are independent of quantity. All right. So quantity, by quantity, I mean how big the size, all right, the size of the mass, all right. So it is not dependent on the size of the particular system or anything uh, that describes the quantity or size of the system is not an intensive property. Whereas extensive property, it depends on quantity. So any property which is used to describe the size or quantity of that particular system, that will be termed as extensive property. So volume will become or is a extensive property then, right? Mass is also an extensive property. Temperature, on the other hand, is a intensive property. You can also understand intensive and extensive property by the fact that if you divide a system in two, all right, then let's say mass of both halves. This is your entire system. If you divide it, initially the mass was m. If you divide the system, each half will have m by 2 mass. So you can distribute the mass. Similarly, if the system has a total volume of V, then when you divide it, then the overall volume will also get divided and each house will have a volume of V by 2. Whereas if you divide the system where the initial temperature of the system is, let's say, T, right? So each house will not have T by 2 temperatures. Each house will have temperature T only. All right. So T becomes now the intensive property. Similarly, enthalpy. Enthalpy, on the other hand, is an extensive property. Enthalpy, the definition of enthalpy basically represented with H. It is a summation of or a combination of two terms, U, internal energy, plus P, V, right? This is how you represent enthalpy. So it is a combination of two other extensive properties. So internal energy is also an extensive property. Volume is also an extensive property. So a combination of these two extensive properties is an extensive property only. So H is an enthalpy is an extensive property. Density, what do you think? Density, is it an intensive or an extensive property? It is an intensive property. Okay. However much water you take, the density of water, that is 1000 kg per meter cube, won't change. All right. Then pressure. What about pressure? Is it an extensive or an intensive property? It is an extensive property. Sorry, it is an intensive property. All right. Pressure, how it is an intensive property. If you again think of like pressure, if you think how big or small the structure is, if you increase the pressure, it will experience the same pressure. So yeah, it is an intensive property. All right. Then energy. Is it an intensive or an extensive property? It is an extensive property. Okay. So better to, brush up. So these concept comes from thermodynamics. And if you still have doubts, I would request you to go back, read some uh, first chapters, like the first law of thermodynamics chapters. There you will get much more clearer insight, all right, about extensive and intensive properties. Then if you divide an extensive property by mass, the result is typically an intensive property. Because as we are dividing by mass is representing the size of the particular system. So we are removing uh, the quantity aspect from the extensive property. So the overall quantity now becomes an intensive property. For example, we saw in one example where we calculated specific kinetic energy, where the kinetic energy K is divided by mass, and we got K hat. So K hat, or specific kinetic energy, becomes what? It becomes an intensive property, whereas K is extensive property. So you can imagine, like, more the mass of the water or size of the tube diameter, something like that, the more kinetic energy will be present in the water, right? But if you remove the mass term, then then it becomes specific kinetic energy, and it is not dependent on the quantity or the mass of the water anymore. All right. Then there is one more term very popularly used in thermodynamics in order to explain whether the variable depends on the initial final state, or whether it depends on the path taken by that system to reach that final state. So this term, state variable, is very important. I think from thermodynamics you will recall it. So this is a MCQ based on that particular concept. The question states, state variable depends only on the path taken to reach the state, the initial and final states only, the rate of change of a process, the time taken for a process. So state variable only depends on the initial and final state of the system. It does not depend on how the system reached the final state. All right. Again, I'll repeat, state variables depends on the initial and the final state of the system. It does not depend on how the system reaches its final state. So let me give you pose a question. Suppose there's a system whose internal energy initially was 100 joules, right? It went through some process because of which the final internal energy becomes 50 joules. Now, through another uh, process, this for process one. Now, through another process, process two. Now, for process two, the initial state contains internal energy of 50 joules, but the process two somehow increase the internal energy of the system to 100 joules. So what's the net change in the internal energy for the system? This is this minus this, 0, right? Because we are now checking the net change in the internal energy from the first initial state to the final state of the system. We are not concerned with the path. Here, path, by path I mean here the processes, or what process had to take place in order to change the internal energy. We are not concerned about it. We are only concerned with the initial state and the final state. Okay, so net change in internal energy is 0. Internal energy is also called, or is one of the state variables. All right, U is a state variable. Similarly, enthalpy is also a state variable. Okay. Now there is another question based on the calculation of potential energy. So give me a minute, right, for drinking water. Meanwhile, quickly have a read, right? So in this question, you are asked to calculate the potential energy. So water is pumped from one reservoir to another, that is 300 feet away. This is reservoir 1 containing water. And the second reservoir is approximately some 300 feet away. First, second. The water level in the second reservoir is 40 feet above the water level of the first reservoir. So let us try to show the change in the water level. So the difference in the height of the water level is 40 feet. And what is the increase in specific potential energy of water in BTU per pound mass? Okay, so you have to calculate conduct these calculations in British units, all right? Like feet, pound, BTU, right? Like that. So BTU is equivalent to joules in SI. So specific potential energy, we know potential energy P is mgh. So specific potential energy is simply GH. Okay. Now, G, or acceleration due to gravity, in British units is 32.2 feet second square. Okay. So specific potential energy is 32.2 feet per second square. So into height, that is 40 feet. And we have to get the answer in BTU per pound mass. So we have to do a conversion. So in British units, there is pound mass and then there is pound force. Okay. So pound force is like Newton in SI. All right. So 1 lbf, or 1 pound force, is equivalent to 32.2 pound mass feet into feet per second square into 1 BTU, is like joule. 1 joule is 778.2 feet into lb force. So we have to remove the or cancel out the common terms. Okay. So we are left with units of BTU per pound mass. And if you do the calculations, you can see 32.2. This is common term. So basically 40 by 778.2. It is 0.0514. This is the specific potential energy in BTU per pound mass. All right. This was quite easy. Only tricky thing was to um, do this problem in terms of British units, because now we are not well habituated or well trained in doing calculation in British units. We are more accustomed to SI units, right? So I'll quickly discuss few important points about internal energy and enthalpy. For a pure substance, internal energy is a function of temperature and volume. Okay, it's a function of temperature and volume. Or if you want to write, you can also write specific internal energy is a function of temperature and specific volume. If you write this function in the form of total derivative, then it becomes d u cap is dou t by dou v cap, sorry, dou u cap dou t, this is partial derivative with v cap constant dt plus dou u cap dou v cap t constant dv cap. Okay. Now this particular term is called specific heat capacity at constant volume, CV. CV is specific heat, or it is also called heat capacity. Heat capacity at constant V. All right. In this term, dou U cap by dou V cap, this term is neglected and is thought to be zero. So change in internal energy, a specific internal energy becomes CV dt. If you take integral on both sides, you will get something of this form. All right. Similarly, enthalpy for a pure substance a specific enthalpy for pure substance is a function of temperature and pressure. Okay. If you similarly write a total derivative for this particular function, you should get constant P dt plus constant T dP. So this particular term, partial derivative of enthalpy with respect to T at constant pressure, is called Cp, or specific heat or heat capacity at constant pressure. Is called heat capacity at constant pressure. Okay, and this term is considered zero at low pressures. Okay, so change in enthalpy becomes Cp dt, or if you take integral on both sides, it becomes final minus initial states of enthalpy, integral T1 T2 Cp dt. Okay, so quickly you should remember that you can calculate the change in internal energy when you are given the specific heat capacity at constant volume Cv. Similarly, if you are given Cp and you need to calculate the change in enthalpy, then you can use this particular formula. So very important to remember. All right. Now you can also do energy balance for open systems. But in this case, we are considering that there is no chemical reaction occurring in the system. For open system, we mean that some mass will go in and some mass will come out. So a general form of the energy balance equation looks like this. So I'll not go into the detail of the derivation, like how this equation came about. You can watch the lectures for more details on that. but this is more general form. Here, we are not assuming steady state yet. So there is an accumulation, energy accumulation term on the left hand side, and on the right hand side, you can see the terms for inlets and outlets, the change in enthalpy, kinetic energy, potential energy, inlet minus outlet. So for the same terms, and then there is energy transfer, Q minus W, net energy transfer. Now, usually we represent the accumulation term in energy, where the final energy is subtracted from the initial energy. And in this term, here we are subtracting the outlet enthalpy with inlet enthalpy. That is why negative sign has come in the front, right? And rest of the term, Q minus W, remains the same. Now, this particular equation can be simplified further if you take some assumptions, like if there is no mass transfer, like it is a closed system, then this particular term M will become 0. So net accumulation will be equals to Q minus W. If the system is in steady state or if there is no accumulation, then delta E will be 0. So what you'll get, uh, change in enthalpy, potential energy, and kinetic energy will be definitely equal to Q minus W. If there is no mass flow as well as there is no accumulation, then simply the equation simplifies to Q is equals to W. And if there is no accumulation, there is no heat transfer, like the system is insulated. Work is also not done by the system or done on the system. Potential energy is also 0. Kinetic energy is also 0. Then you are only left with change in enthalpy delta H hat. So delta H hat will be equals to 0. Okay. So this is an example problem where we are considering an open system, and I'll like quickly show you how we can do energy balance on this kind of an open system. Okay, I'll give you a minute. Kindly have a read. Okay. Okay, so let's start solving this problem. So air is being compressed from 100 kilopascal to 55 Kelvin, where it has an enthalpy of 489 kilojoule per kg. So this is, let's say, a air compressor. Air is entering and air is going out. This the state of the air. Let's consider state 1 and state 2. When it is entering at 100 kilopascal and 255 Kelvin, here the enthalpy, specific enthalpy, was 489 kilojoule per kg. It is compressed at 1000 kilopascal at temperature 278 Kelvin. Now the final enthalpy becomes, specific enthalpy becomes 509 kilojoule per kg. The exit velocity of the air from the compressed is 60 meter per second. So the velocity V2 is 60 meter per second. Here the velocity V1 was 0. Okay. So we need to calculate the power required in kilowatt for the compressor if the load is 1000 kg per hour of air. Okay. So let's put this situation in the energy balance equation. So what is the energy balance equation? Delta E is minus delta H hat plus K hat plus P hat M plus Q minus W. Now, since the air is flowing from the compressor, the accumulation is 0. So delta E is 0. No accumulation. Then potential energy, change in potential energy is also 0. All right. Because like there is, the air is not falling or um, accelerating to a height or something like that. Then Q is also 0 because there is no heat exchange. Then, yeah, that's it. And the mass of the air that is entering is same as the mass that is exiting. So inlet mass, state 1 mass is equals to state 2. So let's consider it as M. So let's consider a basis of 1 kg of air is entering. So M becomes 1 kg. So this simplifies the equation to 0 is equals to minus delta H hat plus delta K hat minus W, or W is equals to minus delta H hat plus delta K hat. So what is delta H hat? It is final enthalpy minus initial enthalpy. So 509 minus 489. So it is 20 kilojoule per kg, and delta K hat is final kinetic energy minus initial. So initial was 0. So it will be just half V2 square. So half V2 is 60 meters square by second square. And since we have to do this calculation in the same units, that is kilojoule per kg. So we have to convert it into kilojoule per kg. So 1 Newton is 1 kg meter per second square, and 1 joule is 1 Newton meter, and 1000 joule is 1 kilojoule. So if we cancel out the common units, so we will be left with kilojoule per kg, and the value will be 1.8. So work is minus 20 minus 1.8, that is minus 21.8 kilojoule per kg. Minus sign denotes that work is done on the air or on the system. Okay. But we have to calculate power. Power is what? Work per unit time. Okay. So work we calculated as 21.8 kilojoule per kg. Now we were told the air load is 1000 kg per hour. Okay. And the unit that we have to get the value is kilowatt. So 1 kilowatt is basically 1 kilojoule per second. All right. And 1 hour is there. So we have to use 1 hour is 3600 seconds. So if we solve this and remove or cancel out the common units, we'll be left with only kilowatt. Okay. And you'll get you'll get 0.61 kilowatt. That is the power. So in this way, you can use the definition of the equation for energy balance for open system to solve this kind of a problem. Now we will quickly learn how to use steam tables by solving these few problems. The steam table looks something like this. This is one steam table. Steam tables are available in your textbook. So this is I've taken from the textbook Elementary Principles of Chemical Processes. All right. And you can see this is table B5, where the properties of saturated steam is given. Here, first column is temperature of the steam. Then pressure is given. And for each temperature and pressure, you can get the values of specific volume, specific energy, and specific enthalpy. When there is saturated liquid water and saturated steam. And for enthalpy, there is another column called evaporation, which is called heat of evaporation, which is basically uh, this enthalpy for saturated steam is subtracted this steam minus enthalpy of water, saturated water. Similarly, you can see similar saturated property. You can see the property of saturated steam for a pressure table. Now, the first column is a pressure. With respect to it, temperatures are given. And similarly, you can get the values of specific volume, specific internal energy, specific enthalpy, right? So it is continuing like this. It's a long table. It goes on to a very high temperatures. Now you can also find properties of superheated steam. Okay, and this is different from the previous tables. You'll see the first column is your pressure, and in bracket there is a temperature written, which is saturated temperature, or also called the dew point in degrees Celsius. And for each particular pressure with respective dew point, you are given specific enthalpy, specific uh, internal energy, specific volume. The values you have to, like, suppose you are asked to find the specific enthalpy, volume, and internal energy for water when it is at 100 degrees Celsius and at pressure 5 bar. You will see this is the values, right? So, but it lies within this particular enclosed space. This means that the water is in liquid state. Any value which lies beyond this enclosed space comes under superheated steam. Okay. So with this brief introduction, I'll let's solve some simple questions using the steam tables. The first question: determine the vapor pressure, specific internal energy U cap, specific enthalpy H cap of saturated steam at 1335 degrees Celsius. So we have to use the saturated steam table, not the superheated steam table. So this is the saturated steam table. So temperature that was asked is 133.5 degrees Celsius. So if you scroll, we are on, it is only 68 degrees Celsius. Then the last is 102 degrees Celsius. So this table B5, where the values are given with respect to temperature, is not going to help us. But we have another table, the same thing, saturated steam, but here it is called the pressure table. We can now follow column 2, the temperature table, in order to find the temperature of interest, which is 133.5. There you go, 133.5. Okay, so at 133.5, the pressure is 3. Okay, if we, let me highlight this entire row. Okay, this is the row that we are interested in for this particular question. What we are asked? We are asked the vapor pressure. So vapor pressure will be 3 bar In specific internal energy, U hat of saturated steam. So if you see, there is water as well as steam. So we have to take this value. It is 2543 kilojoule per kg. You can see units are mentioned here. Then we have to also get the specific enthalpy, H hat of saturated steam. So this is the value, 2724.7 kilojoule per kg. Okay. So these are the values that are required or asked in this particular question. Let's look at another question now. Show that the water at 400 degrees Celsius and 10 bar is superheated steam, and determine its specific volume, specific internal energy, specific volume, specific internal energy, specific enthalpy relative to liquid water at the triple point and its dew point. Okay. So first let's go to the table. The properties of superheated steam was given. There you go. Properties of superheated steam. Now what was the temperature and pressure? Temperature was 400 degrees Celsius. Pressure is 10 bar. So let's scroll down quickly. No, nothing here. Let's scroll down. Okay. So temperature, you can see this is the row is the temperatures. So 400 is not there in the first page, but there you go. 400 is here and 10 bar. This is 10 bar. Okay. So the intersection of this to this column and this row is basically this particular row. All right. Where 10 bar is the pressure, 400 degrees Celsius is the temperature. No, only up till here. Yeah, only up till this region. This is the values that we're interested in. So H hat then becomes 3264 kilojoule per kg. Then U hat is 2958 kilojoule per kg. And V hat becomes 0.307. Which is also in kilojoule per kg. Sorry. So here you can see the units. Specific enthalpy is mentioned in kilojoule per kg. Internal energy, specific internal energy is mentioned in kilojoule per kg, where specific volume is mentioned in meter cube per kg. Okay. So we have to write specific volume as meter cube per kg. Now what is the dew point? You can see the dew point is 179.9 degrees Celsius. Now you can see this particular value does not lie in this particular enclosed region. So there's one thing mentioned. Water is a liquid in the enclosed region between 50 to 350 degrees Celsius. So in this enclosed region, the value does not lie. That means it is a superheated steam. Okay, it is a superheated steam. All right. Next question, question number 16. Determine the vapor pressure, specific internal energy, vapor pressure, specific internal energy, specific enthalpy of saturated steam at 453.05 Kelvin. So the temperature, first we have to convert to degree Celsius. All right. Temperature in degree Celsius is basically 453.05 minus 273.15. Okay. And you should get you should get 179.9 degrees Celsius. This is the temperature at which you have to look at the saturated steam table. So let's go back to the saturated steam table. So we have to use the pressure table only because the temperature table does not exceed beyond 102 degrees Celsius. So if you look at the pressure table, 179 degrees Celsius, 179.9, 179.9. There you go, I found it. So this is the row that we're interested in. Yep. So this is your first is your pressure column. This is your pressure column. This is your temperature column. This is your for steam V naught. Then this is your for steam U cap. And last one is also for steam, but here it's for H cap. So we have to get the values for saturated steam only. So we have to look at these values. So first the pressure value, the pressure is 10 bar. Then specific internal energy is for the steam is 2581.9 kilojoule per kg. Then specific enthalpy is 2776.2 kilojoule per kg. All right. So there you go. You have the values needed for this particular question. So in this way, you can use the steam tables in order to get the values of the quantities asked in the question. All right. You have to use two steam tables. Basically, one is for saturated steam, another is for superheated steam. So for different states of water, as you can see from the phase diagram of water, you can, from there only, you will understand where the subsaturated steam lies, where the superheated steam lies. All right. So this is very easy. These steam tables are available in your textbook. And with this, I'll highlight the references that I've used today to prepare these slides for you guys. And I have taken questions also from these textbooks. If you get access to these books, you can solve much more similar problems that are available. All right. So with this, I'll end today's session and I hope to see you guys in the next week. Thank you for joining.